All right, so in this picture, this is similar to your homework problem. Again, if you want to pick it up after class and redo it, you can. You do not need to have the nullclines in there. That's new for today. But one other thing you do need to have in here that I do not yet is the solution curve itself for those initial conditions, which we've seen you can use DSolveValue to find. So let's go ahead and do that. Let's find the solution curve, the unique solution of this initial value problem next with DSolveValue. So, as I've shown you already, you want to put your equations inside a list first in DSolveValue. The first equation is the dx/dt equation. Type dx/dt as x prime of t. Got to use double equal signs for any solving command in Mathematica. The right-hand side, I could type, based on this, I could type negative x of t minus 3y of t. But since I've already defined f, this function of two variables, I might as well use it. I can just type f of x of t comma y of t like that, once I've got f defined. F being this thing here. Defining with underscores, but once you've got the underscores, once you have the functions defined, then you don't use the underscores anymore. I can also use the fact that I've defined g of t for the y prime of t equation. But you do plug in x of t and y of t into f and g, not just x and y. Mathematica wants you to emphasize these things are ultimately functions of t. X of t and y of t. Put your initial conditions in here as well. X of 0 equals 2, y of 0 equals 1. I'm solving for both x of t and y of t, so I put that in a separate list, and then another comma, and emphasize that t is the variable. This should solve it. I'm not real happy with DSolve and DSolveValue, and it seems like it's different than it used to be. It often leaves the answer in a form that's not real pleasant looking. I guess that's not too bad. Sometimes it's not so pleasant. Sometimes I simplify or expand by doing slash and either simplify or expand at the end. Either way is okay in this case. Neither one is too bad. They're both fine. That's your solution curve as a parametric curve. I could call it C of t if I like. I could define C of t to be this. Not that I have to do that, but I can. If you were writing that by hand, you'd probably use parentheses instead of curly braces. C of t is, in parentheses, 2e to the negative t cos 3t minus e to the negative t sine 3t. And then y of t is going to be e to the negative t cos 3t plus 2e to the negative t sine 3t. So there's how you'd write it by hand. Your solution function is a parametric curve. You can differentiate it. If you do, that's called the velocity vector. I could let v of t be c prime of t, and then I could show you what v of t looks like. There it is. And I could write that out. I could write a c prime, or I could write a v of t equals c prime of t, and I could write that out by hand. Conceptually, we often think of this as being a point and this as being a vector, an arrow, although this one could be thought of as a vector as well, the position vector. Vectors and points have this correspondence between them. Anytime you've got a point, for example, in the plane, you can always identify a position vector with it. And the components of the vector, the first and second components, displacements, match the coordinates of the point. You can even use the same notation for them. We don't always use the same notation in other classes. Like in physics, you use the I hat and the J hat for vectors. In DiffyQ, we actually write our vectors in what's called column form. We write the first component and the second component in columns like that. But there's the calculation. You could do that by hand, I'm sure. You'd have to use the product rule and the chain rule with these things. It would not be super pleasant, but it could be done and simplified to this. You can also find the formula for the acceleration vector as the derivative of the velocity vector, or I could do C double prime of t and look at what its formula looks like. Then I can add the solution curve to the picture, as well as these vectors. Use parametric plot for the solution curve. Use graphics and arrow for the vectors. So let's see. I can put both of those things after ListPlot. That would be fine. So parametric plot. I got C of t defined. I can do that. I'm not doing an animation. I'll just go from 0 to 2 like on the homework. There's your solution curve from time 0 to time 2. Actually, it's not in the lower left like I was thinking. I thought I did that yesterday and it was over there, but I guess I was wrong. So I guess your picture should have looked like this. So if you were confused when I drew it on the board in the wrong spot, you were right, not me. So it should have looked like that for the curve. And then let's put the vectors in here now. Graphics is the framework command for this. There's the basic syntax, and you put stuff inside the curly braces, like thick, red, arrow for the position vector. It starts at the origin and goes out to C of 2. Time 2 I'm talking about here. Got the picture in there? Okay. I do save these on Moodle, and I have mentioned that, so you can download these. I've downloaded recent ones here. There's your position vector. It's kind of small. It's barely an arrow. It's just an arrow. It's like, if we zoomed in closer to the origin, it would look bigger. What about the velocity vector? Within the same graphics and the same curvy braces, I could, for example, do blue arrow. Start the velocity vector at C of 2, end it at C of 2 plus V of 2. V of 2 is the true velocity vector, but I don't want it to start at the origin. I want it to start at the point itself. And to get the right endpoint, if you start at some place other than the origin, you would add the velocity vector to the coordinates of that point. There's a velocity vector at that time. And probably the acceleration vector is going to point down this way, I'm guessing, because the motion is going slower here as time goes by. Maybe not monotonically, maybe not always decreasing in speed. But these arrows are, generally speaking, getting shorter. And shorter arrows in the vector field correspond to slower motion in the curve, because these vectors in the vector field are the velocity vectors at the given moment in time. At this point, for example, the vector field truly looks like that. It's shortened for a nicer picture, which is especially important out here. But that's the true velocity vector for the vector field at that point. What about the acceleration vector? Green arrow, C of 2, comma, C of 2 plus A of 2. There's your acceleration vector. Somewhat down that way, a bigger than 90-degree angle with the velocity vector. When the acceleration vector makes an angle with the velocity vector bigger than 90 degrees, it is true, and I hope somewhat intuitive, that means the instantaneous rate of change of the length of the velocity vector, which is the instantaneous rate of change of the speed, should be negative. So the object should be slowing down at that moment in time. The instantaneous speed's derivative should be negative. If the angle is less than 90 degrees, then the acceleration vector as the derivative of the velocity vector is sort of implying that the velocity vector is going to get a little longer after a short amount of time. You're speeding up. That's what that means. And we can do other things to review parametric curve stuff and review the beginning of the semester. We can, for example, find a speed function. We can look at the formula for the velocity vector. Square this thing, add those squares up and put them in a square root by the Pythagorean theorem, really, and that's the speed, the length of the velocity vector. That's what I'm talking about. You can also do that with something called a dot product, but I'm not assuming you know about that. By the Pythagorean theorem, to figure out the length of this velocity vector, you can take its first component, this thing, and square it. You can take its second component, this thing, and square it. You can add those things and then take a square root. The Pythagorean theorem is what I'm using there. The length of the velocity vector is the speed. As a function of time, what does it look like? Looks like that, which isn't much different than what I just typed. Does it simplify? I think it does. Wow, it simplifies to that. The cosines and sines went away. What do you think happened? Probably some cos squareds plus sine squareds equaling 1 probably happened. Yeah, I'm sure that's what happened after simplification. So that is the speed as a function of time, and that is a decreasing function of time. You can plot it. Plot the speed. That's monotonically decreasing. And the integral of the speed is the distance traveled. I can do the integral of the speed. All this is all good review here. Integrate the speed. Although if I do it indefinite integral, I'm not sure how nice it's going to look. Okay, it's not too bad. That's actually not the distance traveled function, because if you graph that, it's negative. However, so if I copy and paste this in here, graph it, t goes from 0 to 2, it's below the axis, it's negative. However, if I shift it up so that the starting point goes to the origin, which is just doing a plus c for the integral, an appropriate c, then it actually becomes the distance traveled function. The value of this at 0 looks like is negative 5 root 2. So if I just put a 5 root 2 in front of this, then its graph is going to go through the origin. That is the distance traveled function, and it is an antiderivative of the speed function. That's all review. We did that, remember, for the first few weeks of class. Integrate the speed to find the distance traveled. And this is the distance traveled function. Actually, you know, this square root simplifies to just e to the negative t. Right? Taking the square root of e to the negative 2t, you're going to get e to the negative t. That does simplify. So we can bring in all those things too in our looking at the situation. Are those relevant for the differential equations and whatever it's modeling? Well, maybe in some way, but I'm not sure the best way to describe it. I'm trying to just say, you know, the phase plane helps us understand the solutions. X and y as functions of t are oscillating towards 0 in this example. Does this example correspond to a physical model? Well, it's not a mass and a spring model, but maybe there's some other situation that it models. And x and y are oscillating with decreasing amplitude towards 0 is what this implies. As far as the vectors and the speed and the distance traveled, that's just a review of parametric curves. I'm just interested in knowing what happens along this curve as time goes by as a pure curve problem, parametric curve. What is the overall distance traveled as you head toward the origin? I guess that would be an improper integral of the speed. Or the distance traveled as t goes to infinity, which, if you think about it, should be 5 root 2. The entire distance traveled as you spiral in toward the origin, forever and ever, as t goes to infinity, the entire length of that curve is 5 root 2. It's finite, because that improper integral is going to converge. Because this distance traveled function is going to have a horizontal asymptote equal to 5 root 2. You could go out further to see that. 5 root 2 is about 7.07. You see it approaching that horizontal asymptote. Okay, so you can put a lot of things together when doing this subject. With the time we have remaining, let's do an interacting species model again. This was a predator-prey model. Let's do a cooperating, no, let's do a competing species model. So these things are right-hand side functions for a couple different species equations, the RDT and the FTT. R was rabbits and F was foxes before. But maybe we pretend the, what did I say? We should do cooperating or competitive. Maybe the rabbits and foxes, the foxes don't eat the rabbits, but they do compete for the same food. Maybe they all like berries, okay? So they're competing for the same food resources, but the foxes don't actually eat the rabbits. But they have their berries to eat, both of them. And in the absence of the other species, they grow according to a logistic model. So that would be something of the form, take the rabbit right-hand side, something like this, for example. dRdt equals that, ignore the R times F term. That would correspond to logistic growth, with K equal to 2 and the carrying capacity equal to 3, maybe 3,000 rabbits. Maybe since the foxes have a food source as well, berries, something similar works for the foxes as well. Except maybe the coefficient K is 3, and maybe the carrying capacity for the foxes is 2. So in the absence of the rabbits, the fox population is going to have a dFdt equation equal to this on the right-hand side. Oops, it should be F there, sorry. A logistic model with K equal to 3 and carrying capacity equal to 2, maybe that 2 represents 200 foxes. But then this is competing species, so both interaction terms should have a negative sign. This one already does, this one doesn't. I want interaction to be negative for both. When there are lots of rabbits and foxes, they're all competing for the berries, and so they all tend to influence the growth rates of the other species negatively. Maybe the effect is greater for the foxes, say, so maybe I'd have a bigger coefficient there, bigger negative coefficient. Okay? These are the right-hand sides then of dRdt and dFdt. dRdt equals this, dFdt equals this. Is it okay if I don't write that on the board? For some good time. These are the right-hand side functions in F and in G, just like we did with the example that I did put on the board. But these are nonlinear equations. The equations on the board were linear. Nonlinear equations are harder to deal with, but these are still possible to find the equilibria for. Though we're going to have Mathematica do it. I need to set these right-hand side functions equal to 0 and solve for the unknowns to ultimately find my equilibrium points. Looks like there's 3 of them. The origin, 0, 2, which shouldn't be so surprising, and 3, 0, which shouldn't be so surprising. Actually, sometimes with this, there's a 4th one in the first quadrant where R and F are both positive. That can happen sometimes. It's not happening with this particular one, but it can. Let's copy and paste our code from before with the rabbit and fox predator-prey model to look at a picture of the phase plane. But my list plot for my equilibrium points is going to be different. 0, 2, and 3, 0 are my other equilibrium points. Let's just see what it looks like. That's what it looks like. So the rabbit axis in thousands of rabbits and fox axis in hundreds of foxes. You got 3 equilibrium points, and you can see it looks. What does it look like is going to happen in most solutions if you follow the arrows? It looks like most solutions are going to head toward that point, where the rabbit population is 3 and the fox population is 0. Sorry, foxes. Does that definitely happen for all initial conditions? That's not obvious. It might not happen for all initial conditions, and I think it probably doesn't actually. I think some initial conditions where the rabbit population is real close to 0 are actually going to give you solution curves that head up this way, but it's hard to see. Maybe if we zoom in closer, we'll see it better. Instead of going out to 10, let's go to 4 or 4. Yeah, 4. Maybe this will allow us to see that better. Yeah, you see it better. Some solutions with initial conditions over here, you see the arrows are going up that way, are actually going to head toward that point. Now, are they going to interfere with this arrow coming down? Well, not quite. Let's see what happens if the nullclines shed any light on this. Let's add the nullclines to the picture now. I want that on top of the vector plot, so let's see, you can go right here. Contour plot. Can plot these nullclines in here. F of capital R comma capital F equals 0, and G of capital R capital F equals 0. Let's make these colored in a certain way so we can tell which one is which. Let's make the F, actually I have to do contour style instead of plot style, contour style. Let's make the F1 be red and the G1 be blue. The little F1 in red is going to correspond to the RDT equation, the rabbit population equation. That's like dx dt. You're going to cross the red nullcline vertically. Because the RDT is going to be 0. And the blue nullcline, that's going to correspond to G being 0. That's the capital F dt equation, the Fox rate of change. That's the second variable. That's going to correspond to crossing, you're going to cross the blue nullcline horizontally. Where red and blue intersect, you've got equilibrium points. I think the r-axis should also be a blue nullcline. I'm not sure why it's not graphing it. Let's see, maybe if I make, oh, I didn't put a negative point one here, I put a positive point one. That's the reason. There we go. Where red and blue intersect, that is where you get equilibrium points, because that's where both dRdt and dFdt are 0. Maybe I was wrong, actually. I'm glad I did this. Maybe I was wrong. Maybe these solutions in here don't head toward that point. They start to. But you got to cross the blue nullcline horizontally. A solution curve heading up this way is going to cross that blue nullcline, and it's got to cross it horizontally, meaning it's got to cross like this and then head down this way. And if it comes closer to the black dot, it's still going to cross the blue line horizontally, then it's forced to come down this way. I'm glad that happened, okay? Something that I wasn't thinking happened did happen. It is true that for this model, for any positive initial conditions, it seems your solution heads toward that point where the rabbit population stabilizes at 3,000 and the fox population dies off. Now I could tweak the coefficients here, the 2 here, the -1 here, the 3 here, the -3 there to make different things happen. Where maybe they don't both die off, possibly. Actually, I think what commonly happens with these examples is one or the other does typically die off. With cooperating species, that doesn't typically happen. Maybe we should do that real quick. Let's do a cooperating species one here in a second. But this one, it seems that the foxes die off and the rabbits don't. Does that happen in real life? Not necessarily. It's sort of, you know, it's not like physics where you take your equations really seriously as having good predictive value, like to help you send a spaceship to Mars. Did you hear about that engineering mistake from about 15 years ago where they went past Mars because they were using English units instead of SI units? Did you hear about that? they missed Mars and lost millions of dollars on their spacecraft because they were using English units. When some people realized were using English units and other people thought they were doing metric, and it messed things up. So we're not saying these have predictive value necessarily, real precise predictive value. They're more like moral of the story kind of things. One species or the other could conceivably die off. It's not beyond the realm of possibility, is the idea. Of course, in real life, things are more complicated. There's not just two species. There's usually hundreds of species in an environment, if not thousands when you include microbes. But sort of moral of the story kind of thing. Let's quickly do another example, just copying and pasting these code and making appropriate modifications of a cooperating species. I can just change these signs to pluses now. And that would be cooperating species. Now the rabbits and foxes help each other in like a utopia. So they help each other. What are equilibria? Same equilibria before along the axes. One set of equilibria negative. I guess that doesn't really have any relevance for the rabbits and foxes, though. So as far as we're concerned, these three equilibrium points are still the same. Let's see what the phase plane looks like. Now it looks like rabbits and foxes live together in harmony and they both go off to infinity, which is probably not realistic, right? Actually, let's come back to the other example and finish class with one other thing. I will spend more time on this on Wednesday. What about getting solution curves in this picture, as well as maybe position, velocity, and acceleration vectors? Not for rabbits and foxes running around, but for the curve, just for fun. Well, if you try to use DSolveValue, it's not successful. We saw that maybe that product log comes into play, and that's not a nice function that we're used to. So instead, we need to use a numerical differential equation solver. And probably the easiest one for us to use is something called NDSolveValue. Put an N in front of the DSolveValue. And we can, in the documentation center, look up examples. And let's see, is there one that's for a system here? There's for a system. Let's copy and paste this code. Zoom in on that so I can make it bigger. This particular bit of code is for a system and getting parametric curve as your solution. Let me just copy and paste this code and make appropriate modifications. Instead of X solution, I probably want to call it R solution. Instead of Y, probably F solution for rabbits and foxes. With the differential equations, I want R prime of t equals f of R of t, comma, capital F of t. For the capital F prime equation, I want g of capital R of t, comma, capital F of t. I want initial conditions involving R and F. Looking at this picture, what kind of initial condition should we pick? Why don't we pick one of the ones that starts near the origin and heads up this way before coming down that way? That would be the most interesting kind to look at. So perhaps if I pick R to be pretty small, like 0.01, and F to be a bit bigger, like, oh, I don't know, 0.1 maybe. Give that a try. So this is in thousands, so I guess that would be 10 rabbits. This is in hundreds, so I guess that'd be 10 foxes. Solve for R and F. T goes from 0 to 20. It just puts a 20 in here. I like adding the 0 in there. What happened? It did solve it. It's representing the solution in its memory in some way is what this stuff means. In terms of what it calls an interpolating function. This is the R function. This is the F function. You do see the rabbit population is stabilizing toward a value, and the fox population goes up, then down, and they die off. Can we put this together in a parametric curve? Bear with me here. I think I should not have gotten rid of that documentation center. Let's see. Yeah, you can do a parametric plot. In here, I can add the parametric plot for RSol and FSol. There we go, almost done. Plot style. Oh, how about thick cyan? There we go. There's your solution. Heads up. It's got to cross the blue line horizontally. And you see from these other arrows, it's got to head down this way and it heads toward that equal. Okay? Have a good day.